Okay, we are recording. So last day we had looked into various features of eigenvalues and eigenvectors, and we had seen properties of similar matrices, and finally we had stopped with a note of the Schur's triangularization. We had stopped with the note of Schur's triangularization last day. So today we'll be trying to prove the Cayley-Hamilton's theorem. And once we have proved the Cayley-Hamilton's theorem, we'll be going to the next part of today's session, which will be implementing all these algorithms to for different all these methods for building different algorithms of dimensionality reduction and matrix diagonalization. So let's start with the Cayley-Hamilton theorem. Please recall that we discussed that any matrix can be written as a unitary matrix times a triangular matrix and another unitary matrix, which is also known as the Schur's triangularization. This is known as the Schur's triangularization. Okay, so what happened? Why is it not appearing? Yeah, so it's called the Schur's triangularization. Now we'll show that the any matrix actually satisfies its own characteristics equation. So what is the characteristic equation we discussed last day? Recall, it is the determinant of Ti minus A, right? So any idea that why will this be equal to 0? So any idea? So a naive person would say, just put A here. So what will you get? You'll get AI minus A, and you'll say this is 0, right? Because determinant of a 0 matrix is 0. But can you tell me what is wrong over here? This is wrong. Why is it wrong? Any idea? Am I audible? I'm seeing a lag in my this screen, but others are all right, okay? You can hear me, right?
Yes, the screen is lagging.
Yeah. So I'm saying why is it wrong? So any idea why will it be wrong? Why can't I put A over here? Just directly.
That way you are finding the determinant of a null matrix.
No, that you can always do. That will be 0. But if you put, see, T is a scalar, right? So you are, in case of, if it is a scalar, so your diagonals become T minus 1, 1, T minus 2, 2, right? And so on. So how can you put a matrix over here? Can you do that? So it may be obviously, you may find it obvious that you can put T, but you can actually not put T because your T's are along the diagonal and you're finding the determinant of this matrix, and just putting those A's in the diagonal won't work. So what will we do to make it work? So we'll do our what we discussed using the Schur's triangularization. So we know we can, this we have discussed, right? So we have seen, so since it is a n degree polynomial, the this polynomial is an n degree polynomial. So what can we do? We can write it as a product of, what can we write? It is a product of the eigenvalues, right? Yes or no?
T minus the eigenvalue.
Yes. So this will all be the, so we have seen the last day that the eigenvalues, because it's a solution, the solution to this determinant, this characteristic equation are the eigenvalues, right? There's no question about that. So the solution to this equation is the eigenvalue. So you can factorize this way. There's no doubt, right? So next, what we'll do, we will be now if we represent this as a matrix equation, what will it be? So if I go on putting any matrix A, then I can do this. There's no problem, because why can I do this? Because I can write A now in place of T and convert these to these matrices, right? Yes or no? This is a very valid matrix equation. Do you agree? Which was not the case here, where because T was a parameter which was a scalar. Do you understand now?
Yes, sir.
Others. So now what will I do? Any idea? So why did I introduce the Schur's triangularization? Was for purposely for this one. So I introduced the Schur's triangularization only for coming to this, right? So what will I do? I'll be replacing A as UT, U Hermitian, right? Is it okay? If I do that, what can I write I as, like we did last day, to show that any similar matrix have the same characteristic polynomial or the same eigenvalues? What can I write I as if these are orthonormal or unitary matrices?
S inverse S.
So U Hermitian A U, right? Yeah. So alpha times U Hermitian I U.
Then nothing is coming on the screen.
No, it's coming now, no? You can't see?
It came now.
I think that was on your side, but anyways, I'll just do full screen. Okay, so this is allowed, right? So this is equal to I, right? Yes or no? So now what can I do with this product? How can I factorize it? Hello, am I audible? How can I factorize this so that I get a something useful? So you see that I can write. Yeah, go ahead.
We can get that I out. Yeah, because it's the identity matrix, we can get that I out.
So you can write something like T
We can take
minus
the
alpha
common.
I and U Hermitian, right? Is this okay? Because both sides you have this U, you can take the U out without any problem. And here also on the right also you have a U. So you can take U out without any problem. Do you agree? Yes or no?
Yes.
So what will happen to the others? So if you take the product of these, what will you end up with? So I equal to 1 to n. What will you end up with? What will happen to terms in between? You will have a U Hermitian from here and a U from here. So what will be the, okay, it's not here. So yeah, you will have U Hermitian from the left and U from the right. So then what will happen? It will become I, right? So every term you will be factorizing, right? So you will have U, T, U Hermitian, and alpha 2, U, I, U Hermitian, so on, right? So for all of these, you will be, yes or no? For all of these, you will be having something like this. So wait, just 1 second. For all of these terms, yeah. So finally, you can hear me. So for all of these terms, you will be having towards this middle, you will be having U Hermitian U, right? Yes or no? So these will become I. So if this will become I, so what will you end up with? I equal to 1 to n. So I don't know what should I do now. So this is totally ridiculous. Not I'm seeing this is stopping, so on. There's some issue with the connectivity. I'm trying to fix it. Just give me a moment. Just give me one moment. I'll fix this. I'll try to join again. Okay, I think it is fixed now. Let's see. Okay, so you will have all these. If you can hear me now, you will have all these U Hermitian U's in the center, right? So those will all become I. So if you, since you're not interacting, I'll continue. So you'll be left with T minus alpha I, and you will have a U at the end, this side, and U Hermitian this side. Is this okay? This factorization. Now, why is this useful? Can anyone tell me? So T was supposed to be the matrix that had the alpha 1, alpha 2, alpha n along the diagonals, right? And you had something on the top and 0 at the bottom. So I will show you the product of two such side adjacent matrices, and you'll tell me what will the rest of the product be. So let's do T. So T minus alpha 1 I. Do you agree this will be 0, alpha 2 minus alpha 1, and so on, alpha n minus alpha 1, and something on the top, right? Similarly, you'll be having a product with alpha 1 minus alpha 2. This is T minus alpha 2I. 0, alpha 3 minus alpha 2, and so on, right? Alpha n minus alpha 2. Is this clear? What we are doing? So I'm trying to find out this product of these T minus alpha. Am I audible? Anyways, is there any problem?
Yes.
Okay, so what will this product be? These two matrices?
The diagonal elements will get multiplied.
Alpha 2 minus.
Okay, so what will happen? So diagonal, so you see, so do you agree all the elements below this will still remain 0 since it's a lower triangular matrix? So you can check, right? So you see the first element, right? CT11. What will it be? It will be 0 times. So your T11 will be 0 times alpha 2 minus alpha 1, right? Plus all these terms which are 0, right?
Yes.
plus all zeros. So if you multiply these, which will all become 0. So T11 is becoming 0, right? Similarly, what will happen to T22?
0.
Why will it be 0? So you see, so T22 you will get from this row and this column, right? Correct? So it will be 0 times. So this is your sum A12 plus alpha 2 minus alpha 1 times 0 plus all others are 0. So do you see you get 2 elements along the diagonal which are 0, right? Here all are 0 as well. And this you will have something along the diagonal which will say be T lambda 3 all the way to T lambda nn. What will be above these? So for example, what will be this term? What will be term T1 2? Any idea? See, 1 2 will be first row plus second column, right? Yes or no? I'm trying to find these 3 elements. So
This will
1
also
3,
become 0.
correct. So because you will have 0 times A12 plus A12 times 0, which is from here, and plus so on. You will have this going on forever, right? So you will have plus all the zeros, which will come from below this because it's a lower triangular matrix. So do you see that you get this block of zeros, right? So if I keep on multiplying all these zeros next by induction, here I'll be having a 0, right? So next one I will be having a next term, right? Next term, I'll write here next term will be what? Can you tell me what is the next term? So you will have
3 zeros are along the diagonal and rest.
correct,
are
very
zero.
good. So alpha 3, alpha 2 minus alpha 3, and then 0, and then so on. So once you multiply this, what will happen? So you will have a block of, by induction, you will have a block of 3 zeros. This will become 0, and this will become this, and then you will have all the rest terms. So at the end, after n multiplication, what will happen? So it
Everything
will
will
only be
come.
it will become a 0 matrix. So it becomes a 0. So do you see that? So you agree? So PA of T is equal to 0. So can you now, if you understood this Cayley-Hamilton's theorem and the Schur's triangularization, can you prove this statement for a general matrix that we had shown last day, right? What did we show? Let's prove it. Last day we had seen, previous day we had left this, right? We had said PA of T can be written as T to the power n minus trace of A, which is also equal to lambda 1 plus lambda 2 and so on lambda n. T to the power n minus 1 dot 1 to the power n determinant of A, which is also equal to product of the lambdas, right? Can you show this now for a general matrix? And if you can, tell me what to do if you like have the idea. So we will be okay.
We can expand that entire characteristic polynomial by Vieta's formula, and
that you can do, but I want to use you to use the Schur's triangularization and do it, so it will become very much simpler. Yeah, go ahead, Ritik.
A equals to the T equals to A, and then
See, so now T equal to A will not do this. So what is PA of T? It is determinant of T minus I, right? Ti minus A. You agree?
yes.
So we have discussed the Schur's triangularization. So let's see. So Schur's triangularization says that I can write again U Hermitian Ti U minus U Hermitian capital T U, right? So this U is the same because you have a scalar, so it will become I. You agree? I'm just making A to be the Schur's triangularization, right?
Okay.
So what will I end up getting? So do you agree I'll be getting Ti minus capital T, which is a triangular matrix, which we had seen last day? Because this is nothing but determinant of U Hermitian into determinant of Ti minus T into T determinant of U. Do you agree?
Yes.
And since it is a unitary matrix, this is equal to U inverse. So these two will cancel. We had shown this last day. Now you see. So is this triangular matrix? Finding it is very easy, right? So triangular matrix has all these elements, lambda 1, lambda 2, dot, 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 lambda n. Do you agree? And I told you there will be on the top something is star and there's a 0 below. It's an upper triangular matrix with the diagonal being the eigenvalues. So now you see. So if I prove it by induction, so we have shown this is true for n equal to true, right? Shown it is true for n equal to 2, right? You have shown this. Last day only we did a t minus 1, 1 and so on, and we showed that it's determinant and sum. So now let's say it is true for a n minus 1 cross n minus 1 matrix. Right? So I have this equation which is true for this matrix. So you can have PA of T as, what can you write this as now? So you can write this as a determinant. Do you agree? You can write this way. Determinant of this matrix, where you have this is your n minus 1 by n minus 1. You already know the determinant of A n minus 1. This is known to you. This is your A n minus 1. Determinant of A n minus 1 is known by induction, right? And this is T minus lambda n. And you have some stars over here, and by this Schur triangularization, you will have something like this. Agreed or not? This is so I'm just expanding a n by n minus 1 cross n minus 1 matrix to a n cross n matrix. So do you see that now now you can understand what I will do next? Now I can easily calculate the determinant, right? I can just take this T minus lambda n, which I was not able to do before, into determinant of A n minus 1. This is the determinant of A. Do you agree?
Yes.
Others, is it okay? So the last row is 0. So I will just expand about this. So Schur's make it so easy for me. So what will this term become? T to the power n minus 1 plus, or rather minus, your summation of lambda i's I equal to 1 to n minus 1, t to the power n minus 2, and so on till determinant of A n minus 1, right? So now do you see what our claim was? So this will become nothing but t to the power n minus summation of lambda I equal to 1 to n, t to the power n minus 1, and so on till minus 1 to the power n, determinant of A. Do you see why it happens? So you will take the product this way. You will take this product, this multiplication with this. So you will get a minus lambda n t to the power n minus 1, and then you will sum this up with this finally. And how will you get the determinant? You will take a product of this with this one, right? So lambda to the power n, lambda n into determinant of A n minus 1, which is nothing but determinant of A. Do you agree? Correct?
Yeah.
So others, it is okay.
Yes, sir.
So true for n and n minus 1. So true for all n. So we have proved the claim that the determinant will be the product of the eigenvalues and the so this was, we know, lambda 1, lambda 2, dot, 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 lambda n, which we had shown to be the determinant of n minus 1. So this turns out to be lambda 1, lambda 2, dot, 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 lambda n. So we have been able to show that. Correct. So let's go about doing the next thing, which is very easy. So there is a theorem or the theorem that is related to the Cayley-Hamilton theorem, which says that any AK can be written in terms of all the terms up to n, right? Up to n, all the terms after that can be written in terms of an minus 1. To give doing some such examples in your board exams? So for example, you have PA of t given to you this way, right? So we already know that PA of 0 is something like this. So can you say that we can find A inverse from this? Can we find A inverse? So say the P. So first of all, tell me what is the size of this matrix? Size of A. Any idea?
2 by 2.
Why?
Because the order of it is 2, and if we
So
have 2
degree of the
eigenvalues,
polynomial is good. So degree of the polynomial is 2. So that gives me the size of the matrix as we have seen before. So now how will you, this was your staple equation, at least in ISC, this was given every year. So A square minus 4A plus 6I, and this is equal to 0, right? So I just want you to warm up with this. So what will you get? A into A minus 4I will be equal to 6I, right? Minus 6I. So do you see A into A minus 4I by 6 is equal to I, right? So can you say A inverse is A minus 4I by 6, right?
yes.
So see, we have been able to write it in terms of A to the power 0 and A to the power 1, where n equal to 2, as we had said. So let's do one more example. Let's try and write A cube. So how can I write A cube? Any idea? A cube. So how can I write A cube in other terms? Terms of the A square, A to the power 1 and A to the power 0. Simple, right? So see, we have PA of t or PA of A as A square minus 4A plus 6I, right? Which has to be equal to 0. We have shown in the Cayley-Hamilton theorem that the matrix satisfies itself its characteristic equation. So what will I do now to get A cube? I'll multiply A both sides. So I'll multiply A, I'll get A square minus 4A plus 6I is equal to 0. So what will I end up with? A cube minus 4A square plus 6A equal to 0. So what will I have? A cube is equal to 4A square minus 6A. But I have got it in terms of A square and 6A. So now what will I do? To get it in terms of I and IA?
Substitute A square.
Yes. Substitute A square. Very good. So A square is 4A minus 6I. So 4 into 4A minus 6I minus 6A. So what do you get? 16 minus 16A minus 24I. Is this okay? So similarly, do you see for every A to the power n, you can write this way, right? Now we'll see a general case. A general case for the inverse of a matrix. So this I will tell someone of you to prove it now. So what am I saying? Say your PA of t. So let us write it down. I'll just copy this thing and then we'll be doing it. Okay. Or here only we can find, right? So, okay. So how will you prove this? So I'm saying PA of t is some polynomial. That is the characteristics polynomial, right? And we want to show that there exists a QT given by this polynomial where t to the power n minus 1 and so on by a0 where q then QA is A inverse. How do you think I'll do it? So we'll do something like PA of A is again equal to 0, right? Yes or no? So you'll get a to the power n plus correct.
Then we take a common out of both terms.
Very good. So we'll take a common, but we will have to be a bit careful. We cannot take a common directly because we also have a, so we can do something like this, right? We have a
Yeah.
I, right? So what will I do now? I'll take this to the right and I will have minus a naught I. And then I'll take a common as Ritik is telling me. Plus summation of I equal to 0 to, or rather I'll write 1 for the time being, to n minus 1 ai into a to the power of I minus 1, right? So I will be equal to a into a to the power n minus 1 summation of I equal to 1 to n minus 1 ai a to the power I minus 1 by a naught. So what is, so do you see? So if we write a polynomial qt equal to t to the power n minus 1 plus summation of I equal to 1 to n minus 1 ai t to the power n minus 1 or I minus 1 by a0, then QA of this is equal to A inverse, right? Correct?
Yeah.
Others, okay? Just taking in a taking common and expressing this in terms of a polynomial. So with that, we come to the end of the basics of matrices. Now we'll be going, I'll give you a short example, and then we'll be going to, so we have today planned unitary matrices, couple of properties. That's it. And then I'll do Gram-Schmidt, which is which is making unitary matrices. And then we'll do normal matrices, and that's it. That will complete with PCA, and hopefully we'll be able to do it in one and a half hours time. So let's start. So how do you think we'll be doing this question? So eigenvalue decomposition of this. So we have already done this just to give you the motivation of how to. So I told you last day we'll be solving one question to help you not only revise finding null spaces but also eigenvalue eigenvector solutions. So A is this one. So how do I start off? I will be taking determinant of. See, I can do both t minus ai and both lambda a minus lambda I as well. I'll do this, or we can do the other way as we have discussed. So this is what we'll be doing, right? We have seen this 100 times. No. So what will be my equation? Determinant of 1 t minus 1, t minus 4, t minus 3, 0 minus 1, 2, minus 1, 0, 0, right? So what will be the determinant with respect to what will I expand? Can you tell me? There's the intelligent expansion that you always have to try find out. I'll expand with respect to this, and we have zeros in this column, so we will not be requiring any more terms, right? Yes or no?
Yes.
So t minus 4, t minus 3, minus 2, minus 1. So what will I have? I will have t minus 1, t square minus 7t plus 12 minus 2, which is equal to t minus 1. So this turns out to be 70 and this will be 10. So it is t minus 5 into t minus 2, right? So what are the eigenvalues? Lambda equal to 1, 5, and 2. Clear up to now?
Yes.
So I will want to ask you one question. Will this be unitary? Will this be diagonalizable? And if it is yes, and why? We have shown an identity last day, inequality that says that. So they are unique eigenvalues, right?
Yes.
So your algebraic multiplicity we saw was equal to greater than equal to geometric multiplicity, right? Which has to be lower bounded by 1. You cannot have 0 as a geometric multiplicity of a vector,
Yes.
of an eigenvector, right? So since this is 1, your geometric multiplicity will also be equal to 1. So you will have all unique eigenvectors. Do you agree? There will not be any what is it called, deformity in the matrix or the eigenvectors, right? Correct?
Another.
Yeah.
We have this identity m greater than equal to gm, and the geometric multiplicity is lower bounded by 1.
It has to be, right? So you have an eigenvalue a minus lambda I, right?
So here we have algebraic multiplicity as 1. So geometric multiplicity has to be 1.
Yes.
So that means that we will get, for each eigenvalue, we will get one
Exactly. For each
unique eigenvector.
unique eigenvector. Correct. That's why your S will exist. That's what I'm trying to come at. So null space at least must have one vector, right? That's why. Because you are solving as the null space equation, right? You're solving a minus lambda I to be x to be 0. So it must at least have one solution, right? Great. So now what will I do? So first let's find the eigenvector for lambda equal to 1. So what is the matrix? So a minus lambda I will do as I have told you many times. So what is the solution? So it's a minus lambda I times x is equal to 0, right? This is your eigenvector solution. Do you agree? So x has to be in the null space of a minus lambda I. So you have to find the null space of a minus lambda I. Clear? So what is our goal? To find the null space of a minus lambda I. So what is a minus? So a minus 1. So you will have 1, 3, and 2, right? 1, 3, 2, 2, 1, 1. Can you tell me without even finding anything, jhatak se, what will it be? Without even thinking. It should not, you don't need to compute the eigenvector for this. Very simple. So generally you will start off with a pivot. Yeah, go ahead. And then you'll go downwards. So, but here you don't need.
Here it should be 0.
0 cannot be an eigenvector, right? It's a trivial solution. Isn't it? 0 you can't have. No question.
Zero minus 1, 1.
So you are missing out on the easiest of the lot. So can I have 1, 0, 0? Oh, you're saying 0 minus 1, 1. So that is true. Let me just check. That is true. Let's see. So for with respect to 1, I don't know why, what happened in this equation. So is it not right? 1, 0, 0. 1, 0, 0 is not giving me 0. Oh, sorry. Oh my God. Right, now you have to tell me. Now you, of course, you were right. So these two will be the pivots, right? This is your A minus I, right? A minus I, because you have lambda equal to 1. So I had 1 here, not 2, right? So you have 0 in the first column. So what will the eigenvalue be? So this is your F and this is your I. Just putting 1 0 0 will do or not? Is this okay? 1 with the first column, which is all zeros, and the set 2 columns I'm going to put 0 anyways. Is it clear?
Yes.
Yes.
So it's the eigenvector is this. Next, lambda equal to 2. Then what will be the matrix for the timing? Can you help me if you have noted it down? So we can subtract 1 from this. -1, 2, and 1. 2, 1, 1, 0, 0, 0. This is your A minus 2I, right? Correct? I'm subtracting 2 from the diagonals. So you get 1, 2, 1. Happy? So what do I do now? So what is this? What are the steps that I told you to follow to compute the null space for a non? So first step would be to convert the diagonals into ones, right? And everything below it to the zeros. You recall? So first step, what will I do here? I'll multiply row 1 as -1 into row 1. Agreed?
Yes.
Without computing, can I say something? I have
You
not
can.
computed.
No, you can say, yeah.
1 minus 1, 1 does it.
1 minus 1, 1. Yes, it will do it. I don't. Oh, is it? I don't. 1 minus 1, 1. 1. So it's 1. Yeah, I think so. It will do. It will do it. But have we calculated it correctly then? Just check once. Yeah, so it's correct. So 1 minus 1, 1 will do it. So, but okay, I will do it because it's very simple to calculate. So you will have a 1 minus 1, 1 will be a eigenvector. So why is it a eigenvector? Because you 1 times minus 1 0 0. Then you will have -1 times 0 2 0 plus 1 times 1 2 1, right? This is equal to -1 plus 1. And then you have 2 minus 2. And you have -1 plus 1 equal to 0, right? This is what is the step that Brahmajit did in his head to come up with this, right? Yes or no? So let us do the third one. So third one is lambda equal to. So this is equal to lambda equal to 2, lambda equal to 1, and say lambda equal to 5. So lambda equal to 5, let us try and find out. So what is A minus 5i? A minus 5i is, can you tell me the matrix? -4, subtract -3 from this. Is this okay? And don't, now we'll compute this, otherwise we will not have practice. We will do the steps one after the other. Is this okay? So I've subtracted 5, this is -4, this will become -1, and this will become -2. Correct. Now what will be the steps? Now tell me what is the first step that I'll do. See, the first pivot that I have is already 0. or everything below it 0 is right? Yes or no? Please follow the steps. Probably the last time I'm going to compute the null space, which is one of the most important questions people will ask, right? Everything is below it is 0. So what will I do to the first row?
We'll leave it as it is.
No,
We'll take
yeah.
minus 1 out. We'll take minus 1 out. And
Yes,
see that
so minus 1/4 I will multiply to the first row, right? I want always ones at the pivots, and 0, I want only zeros. I want something like U and 0, row reduced echelon form, right? So I want to have, and I want ones at the diagonals. I want is U0 plus ones at the diagonal. So how will I make the diagonal -4 1? I will divide by -4, right? So this becomes 1 0 minus 1/4. Agreed? So I'm doing row 1 as row 1/4. Correct or not? And then row 2, what will I do? Tell me now what is the step? So first column is done. So next pivot is which one? This one, right? Correct. So what will I do now? Next step. It's evident from the matrix itself. What should I do?
multiply with -1.
No, not required. First tell me what, first try. Yeah.
Row 3 equals to row 3 plus row 2.
Row 3 equal to row 3 plus row 2, and then I will do row 3 equal to -1 into row 2 equal to -1 into row 2. These two steps I can do, as Ritik is telling me. So if I do this, so I'll get, first I will get 0 0 0. This is what I desired. So I've got this, what I desired beginning, and I've also got -1 2 0 1/4, right? Yes or no? Next, I have also multiplied -1, so this becomes a +1 and this becomes a -1. Agreed? So carefully doing the box with green so that you can see. So this is okay, right? So next, you tell me what should I do with the, which one is your identity matrix, which one is your F matrix? So you recall, right? So we had said once we do a row reduced echelon form, I will have an I will have an F, and I will have zeros. And in the solution to the null space, what will I do? Someone? How will I get the solution to the null space from this general form?
Minus F and I.
Minus F and I. So tell me which is the I matrix and which is the F matrix here. Try to identify it. Do you agree this is the I matrix? We have the pivots.
Yes.
And this is your F matrix. So what should be your eigenvector from this? So in place of all the dependent variables, so you will place the F in place of all independent variables, right? So place it. Tell me what is F, where will I place? This is your F, where will I place the F? Ritik, you told me the answer, tell me. So it will be +1/4 and 2, right? So you're going to have only one here, one, because your rank is 2. So you only have one dependent vector, yes or no?
Yes.
And I'll put 1 in the dependent vector. So you will be putting 1 0 zeros identities in the place of the dependent vectors, right? So steps, what will you do? First step is putting the, so if you had one more column, what would you have done? You would have put 1 comma 0, right? And 0 comma 1 have to get two values, as we did that day, remember? So if you had, so here you have only one column. So if you had, say, 1 0 0 1, and then you had, say, a column C1 and a column C2, what would have happened? What would have I done for this? So first tell me what would be the dimension of the null space in this matrix? How many dimensional null space would I have?
4 rows and 2 columns.
Null space, what is the dimension? So this is 4 columns, right? So what is the dimension of the null space? It's n minus r, right? What is the rank here? So 4 minus. These two are the null space dependent vector, yes or no?
Yes.
So what would be the null space vectors here in this case? It would be, so in this case, I will be putting 1, 0, right? If I put
Yes.
1, 0, what will I put in this place? Minus C1. Do you agree? If I put minus C1, what will I be left with? I'll be left with, when I multiply I comma C1, I will be getting a C minus C1, and you will be having this column from this one plus C1 equal to 0. Agreed or not?
Yes. Yes.
And then what will be the second one if you have understood? This is your vector v1, so c1 plus c2 times, not c1, so lambda 1 lambda 2 times. So what will be the second eigenvector?
C2
Null.
minus C2 and 0, 1.
Minus c2 and 0, 1. Very good. That's it. So you have understood now. So this is your eigenvector, right? So I have put. So what would be the just scale this one? So you will have 1 by 4 will be 1, 8 and 4. Yes or no? You can always scale the eigenvector, so it will still be an eigenvector or not. So is it yes? So my new matrix of the 3 eigenvalues and eigenvectors is left with. So I have my S matrix as 1, 0, 0, 1, 8, 4 and 1, minus 1, 1. And what are the associated eigenvalues of these? They are, for the first one, it is lambda equal to 2. So this is for the last one. Lambda equal to 1 is for the first one. Last one, lambda equal to 2. So what will be the diagonal matrix? So you remember, right? So we had said that if it is existing, so we will have we showed this is diagonalizability last day. So what would be your lambda matrix here? Tell me. 1, 5, 2, right? Yes or no? Not clear? Let's write it fresh somewhere here. So we have found the 3 eigenvalues as eigenvectors as this matrix, right? I have stacked it. I have stacked the 3 eigenvalues as columns in this matrix. So what did we do last day? So we said that AS was equal to S into some diagonal matrix. Yes or no? Which contained the eigenvalues, because you had where you had stacked x1, x2 and xn, and you had A. Again, I stuck anyways. Yes or no? Is this visible now? We had seen this, right, yesterday, last time, Sunday. So AX is equal to lambda x, yes or no? Similarly, AX2 is equal to lambda 2x2.
Yes.
So what will I have now? A matrix. So what would be my decomposition? Tell me. So my A matrix, I'll be putting 1 0 0, 1 8 4, 1 minus 1 1. What is my lambda matrix? These are the
1,
eigenvalues,
5,
right?
2.
These are the eigenvalues will be along the corresponding eigenvalues. And then I have given you S inverse. You please calculate this at home. I just did not want to waste time because we already did this exercise once. So you'll be augmenting the matrix and calculating the eigenvalues. 1 0 0 minus 1 by 4, 1 by 12, and 1 by 3. Minus 3 by 4, 1 by 12, and 2 by 3. Right? So this is S lambda S inverse. Correct? So as we told that any matrix which is diagonalizable can be written in terms of this product. Is this clear? So after this example, is this working clear? If it is clear, I'll start off with more abstract concepts. So we have with this, we end what is called the computational part of our linear algebra. Now will be only applications. Okay, so let's go to what is called unitary matrices. So yesterday or last day we discussed unitary matrices as orthogonal or orthonormal matrices, right? Special cases we had orthonormal matrices. Recall? So for orthonormal matrices, we say a K vectors are orthogonal or say orthonormal to be if and only if. Oh, in this case, it's orthogonal because I've not said one. Orthogonal if all of them are 0, the dot product between all of them are 0, and with the self is equal to the norm. We'll see what is a norm, but it's a Euclidean distance, right? So you recall x dot x in your school days was the norm square of the magnitude of the vector square, right? So just consider that this is the distance. It will be the distance, agreed? Dot product is nothing but the product x1 square plus x2 square and so on. This is the distance. Good. So next question is, if you have understood, since there's no question, so we have understood what are orthogonal matrices. Now I have to prove that every orthogonal matrix in Cn has linearly independent columns. How do I prove it? So what would be my first step? What would be my first observation? So your orthonormal matrix will have u1, u2, dot, 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 un. What is the dimension of all of these vectors? First question. Yeah, go ahead.
N.
So UIs are n. So why is it orthogonal? Because UI transpose. Here we have said orthogonal, so there's not a problem. We can put transpose, but I'll be putting Hermitian today. Hermitian, you're comfortable with me putting Hermitian, right? Hermitian, you can figure this out as a transpose for the complex numbers with the conjugate being used. I have already told it last day. So Hermitian would be U transpose and you will take the conjugate. That means Aij will be converted to Ij bar so that you can have the whole square forms, right? As we know, Aij into Aij complement is nothing but the norm square, which is mod square, which is not the case in case of real numbers, but in complex numbers, we need to take conjugate. Is that clear? Or do I need to go back again to complex numbers and tell? Is it okay, right?
It is okay.
Yeah. So I'll be using this ui, Hermitian ui as uj as 0. This is all right. This is a property I'll be using throughout. And I will be also using ui, Hermitian ui will be equal to 1, correct? I'll be using these two properties. Now tell me, to prove that they're linearly independent, how have we gone about doing this last 2 days? We took a very simple approach. What did we do? To prove that they are linearly independent, we started off saying that they are dependent, right? And then proved by contradiction. Yes or no?
Yes, by taking linear combination.
Correct. So here, what will I do? Try to do one question yourself, then you'll be feeling good. So let me write this at the end of the page. I'll tick this so that it is done. Okay. Now tell me, so you have, so I'm telling that u1, u2, dot, 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 un are dependent. Say, so by contradiction, I'll say u1 through un are dependent. Now what will I do? As you were saying, I'll do some alpha I uy equal to 0. Yes or no? If they're dependent, I will have a solution like this, which is alpha I uy equal to 0 for all I from 1 to n. Correct? Next, what will I do? Now tell me, there's a very simple, it should be catching your eye immediately. What should I do now? Tell me, it's very simple. So if I take the dot product of this vector with uj, what will happen? I will have alpha I uj Hermitian ui for I equal to 1 to n. Now you should be able to tell me instantly. I've done all the steps. What will happen? For all j. This is just the definition. Tell me. Uj and ui are, if I not equal to j, they are?
0.
Yes, they are orthogonal, right? So therefore, uj Hermitian ui is equal to 0. So what is the only term you will be left with?
The UI
No,
Hermitian is true.
ujj, right? So this is what you'll be only left with, yes or no? So which is equal to 1, and you're saying this is equal to 0. What does it mean? Alpha I equal to, I have written alpha I, alpha j equal to 0, right or no? Correct? Correct, yes, no, not clear, something?
It is
Yes,
clear.
that alpha
Yes.
started with 0.
Yes, so for all j, it will be true. So do you see that it is only, thus they are all independent. Good. So we have only 2 topics to discuss before we go to the applications. So we'll do them one by one. So we have shown that for unitary matrices, all the columns are perpendicular. So now you tell me, how will I prove U Hermitian is equal to U inverse? So do you see what will be this? Let's write it down. So this is number 1. U1 bar Is this okay? Correct?
Yes.
So only the, do you see the only the diagonals will be uy squared, u1 squared, u2 squared, and un squared. Correct? Which is nothing but there, since they're orthonormal as well, this is equal to 1. Do you see there I? For all other combinations ij, this combination, this is the element ij will be nothing but uy Hermitian uj, which is equal to 0. Do you see that? So you have u Hermitian u is equal to the identity matrix. So what can you say from that? U Hermitian is equal to U inverse. Proved or not? Right? So they have, this is trivial. Okay. So how can you say U Hermitian is unitary? This is also trivial. Just tell me without any calculation. From this property, you tell me without any calculation. So I want you to do, just use abstract algebra to do this without just algebra. So we said that U Hermitian U equal to 1 means U is unitary. So what will I do? To show that U Hermitian is unitary. It's simple only, no? So if I consider, yeah,
We can do the inverse of U Hermitian. So that is the thing is that U back.
correct. So if I multiply, what will happen? So I have said U inverse is equal to U Hermitian. So I can also write U inverse is equal to I, right? So I can write U Hermitian is equal to I as well. Yes or no? So your U Hermitian is also unitary. Correct? As you told Promojit, this is right. So third question is both row and column are orthogonal. How do I do that? See, column I already know, right? So I have known that u1 dot u2 un. I have seen that they are orthonormal by using a U Hermitian matrix and showing that equal to 1. But how do I show that rows are orthogonal as well? So they have rows, say R1, R2, and Rn. How do I show that the rows are also orthogonal? The columns are by definition orthogonal. So how to show rows are orthogonal? Ramojit, your idea only will hold?
And the transpose.
Yes. So you will do, instead of U Hermitian U, we will do U Hermitian. Right? We have seen in the previous part B that it is true as well. So if we do U Hermitian, what is this? So do you see U is row 1, row 2, row n, and U Hermitian is row 1, row 2, row n. And I say that this is equal to I, which means row I, row j row j is equal to 0 and row I equal to 1. Is it okay? Others? So rows are orthogonal as well. So if this is okay, let's do the fourth question. So they are said to be unitary invariant. So Euclidean norm is said to be, what is Euclidean norm? It's the distance norm. Distance, normal distance, we are normal distance. normal, x square, y square, z square distance. So just roughly, we will see norms tomorrow or day after, depending on the next session. But can you show me that they are unitary invariant without even knowing about the norms? So number 4, I said ux norm is equal to the norm of x. So this is an intuition that you must have. So once you take the linear combination of a columns of a unitary matrix, the energy in the vector does not change, right? Energy in the vector or the length of the vector does not change in Euclidean space or our Earth space on taking linear combinations of orthonormal vectors. Correct? So now how do I prove it? The intuition is clear, right? So the proof is simple, quite simple. So what is ux squared, norm squared? What is, just to recall, what is x norm squared, Euclidean norm squared, which you popularly know as this? Yeah, tell me.
The length of the vector.
Well, how do you write it in terms of the transpose operation and the dot product?
UUT. Sorry, should I write it?
No, I'm telling a dot product. How can you write this norm length as a dot product? So you have a vector v. How do you write v's length as a dot product? It's nothing but v transpose v, right? We discussed it so many times last day. Yes or no?
Yes.
So v dot v is nothing but the length of the vector times length of the vector times cos theta, right? The cos theta is 0. Correct? This is how you define dot product, right? So this is x Hermitian x. So what will be ux norm? Norm of ux? Ux Hermitian. What is this? X Hermitian. So you know transpose and Hermitians are the same operation, so they will be exchanging. What is this? Identity. So you'll have x Hermitian x, which is nothing but norm square of x. Is it true? Right? Is it okay? Okay. It's clear. So I have just noted it down over here as we have seen before. So if S is unitary, A equal to U Hermitian, they are called, what are these called? We had seen A equal to S, B, S inverse, and showed that they were an equivalence relation. What was this called? A was known to be similar to B, right? Correct? Okay. So what? So if it is similar to B, so what will this be called? This is called unitarily similar. A is unitarily similar. So why do you think this is helpful? We'll see in which case it is unitarily similar, but will be in a moment time. So, but can you tell me how is it useful? This is useful because we don't need to calculate S inverse, right? It's just U Hermitian is equal to U inverse. This is why it is useful, right? Is this clear? Unitary similarity. We'll be using this. Yes, we will be using this now in the normal matrices. Before that, I'll give you a small example of what is called a Gram-Schmidt. So Gram-Schmidt, the objective is given n vectors which are independent, comma, we want to orthogonalize them. So how do you think we can do that? So let's start with two vectors, right? And then we can go on to n with induction. So I will say that I have been given n independent vectors and I want to create a basis in orthogonal basis vectors, right? Orthogonal basis vectors are easy to work with, yes or no? If you have orthogonal vectors, you will not be able to do, you will not be requiring to do S inverse if it's a matrix. So just equal to S Hermitian for orthogonal or orthonormal, yes or no? So if we are able to find orthonormal matrices, it's half the battle done, yes or no? Right. So here we'll be doing something what is from you have say two vectors like this. So I will convert these vectors. I'll rotate them in such a way such that it becomes orthogonal. I have three vectors. I'll rotate three vectors I may have this way, but I'll finally have this vectors I can have. But finally, what I'll do is I'll rotate them in such a way so that where is it? So yeah, so that I get all of them to be perpendicular to one another. Right? So one is into the plane, one is this side, and so on. So how will I do that? So let's start with two vectors. So first vector do that I have. So do you agree that all my vectors have to be unit vectors? All my vectors must be unit vectors, right? Then only I'll get identity matrix, isn't it? Otherwise, I'll get the norm around the diagonal. Do you agree? Okay.
Yes.
So what should be the, how will I convert a vector to its unit vector? I'm being given this v1. How will I convert? So step one, I have this v1. What will I do to make it a unit vector?
We divided by its length.
Correct. So it's unit vector, which I'll be indicating by tildes over here. So this is my orthonormal basis. So for complex numbers, you have something called as householders matrices, but we'll not go into that because anyways, people are not interested. So it's okay. So we have v1 as, what will I write? v1 by mod v1, right? Correct. So now I can work with v1 tilde. So how will I work with v1? Say I have this. What do I have? Yes, I have a placeholder s where I'm storing v1 tilde. So you are writing a program and you stored your v1 tilde over here. Next is I want to fill the v2 tilde, which I'll get from v1 and v2. So I'll be getting v2 from v1 and v2. So how will I get that? So I will be taking one vector at a time. It's sort of a ON complexity algorithm based on the number of objects you are going to parse. So how do you think I will be? So I have v1 tilde now. I have v1 tilde and I have a v2 vector. So tell me now, how will I convert v2 vector into v1 into a vector like this, which will give me v2 tilde? Any idea? We have done this in projections, recall. Recall, we have projection matrices and so on. We have done those things. So what will I first do? How can I get a perpendicular vector to V1? Right? This is so easy.
We
This is
do a dot product so that it becomes 0.
So if you do a dot product, you will get this, right? Yes or no? V1 parallel you'll get, right?
For perpendicular, sorry, we do a cross. Sorry.
No, that you will get in the out of the plane only. I don't want out of the plane. I want in the plane of V1 and V2.
Then we can do a dot, find that angle, then break it up.
So how do you do that? We have done that last day. So if you have, so simple, na? So if you have this error vector over here, right? So error vector is perpendicular or not? It is perpendicular. So V1 projected. So I'll write it this way. V1, V2 projected V1. So VP1 means vector 2 projected using 1's unit vector. Okay. So what will I do? I'll be doing something like a V1. This is your V2, right? Writing VP1. This is your V2. Sum of two vectors. Agreed?
Yes.
So what is your E? Error is V2 minus VP1. So V2 is V2 only. What is VP1? So I'll write error as E2 here because it's the error of the second vector. Right? So what is VP1? V2P1 dot product of what is this?
Dot product of V2 and V1.
So V2 transpose, V1 transpose. This is the length that you will get, right? Into the vector direction, right? Which is a unit vector in our case now. Agreed? No doubt. So you will get V2 transpose V1 tilde. This is the scalar, the length of the dot product into the direction of the dot product, right? So this is going to give you E2. So now how will I get V2 tilde? Which is a unit vector. This is not guaranteed to be a unit vector, not a unit vector. So how will I get the unit vector? I will do E2 by mod E2, right? You only told me. Correct?
Yes.
So step 2. So we have done for V2. So number third, what will I do? Say for the third matrix, third vector, what will I do? So I will subtract errors from, what will I do? So say I want to generalize it, right? At the end of the day, I have two vectors, V1, V2, and one is out of the plane, right? I want to get the third component. How will I get it? So I already have the two perpendicular components, right? So this is say out of the plane. V3, V1 tilde, V2 tilde. So what will I do now? How will I get V3 tilde? So I will take the, what will I do? I'll subtract both the components of V1 and V2, correct? And I'll get the perpendicular component from V3. Yes or no? So if I want to have this perpendicular component, what will I do essentially? I'll be projecting similarly V3 or the error 3, which is from the plane. This is the error vector from the plane, right? Which is perpendicular from the plane, which is some linear combination of the first and the second vector, right? So what will I do? The error vector E3 will be nothing but V3 minus V3 transpose V1 tilde into V1 tilde minus V3 transpose V2 tilde into V2 tilde. Yes or no? I'll subtract both the components to get the third component. So you will be ending up with V3 tilde as E3 by mod of E3.
Can you just explain this part again? How you got E3?
So E2 is clear, right?
Yes, E2 is clear.
So for E3, what do we want? So I already have two vectors, right? I have one vector. I have one vector which is called V2 tilde. I have a vector V1 tilde, right? And the angle between them is 90 degree. Yes or no? Okay.
Yes.
And then I have one vector that is in the, it is out of the plane. Correct?
Yes.
So what is the goal? Our goal is to find this E3, right? Yes or no?
Yes.
This is the, we want to find the perpendicular vector. Do you agree?
Yes.
Okay. So this you can write, what can you write V3 as? You can write V3 as E3 plus this vector, say some x. Yes or no?
Yes.
Sum of two vectors. So what is, how can you write x as?
V1 tilde plus V2 tilde.
Not always. There will be components, right?
The components.
There will be components of, there will be components along this line. And you will have a component along this line, right? Such that you have this. And whose component will you be taking? So one would be the component.
V3 dot V1's component will be taking. Right.
Correct. So you will be, this is nothing but what?
That is
This
V3.
one.
That is V3.
V3
Over V1 tilde.
V1 tilde V3. And this is V2 tilde V3. So you see there are sum of these two. So your, this is your x, right? V3 V2 tilde V3 plus V1 tilde V3, right? So you take this side. So do you get what you desire, E3 or not?
Yes.
So along all the components that you already have, you will be taking components and removing the component with respect to that. So if you have a plane which has two perpendicular components, right? And you remove the two perpendicular components, you will be left only with the perpendicular component to that plane. Yes or no?
Yes.
The idea is, so for example, say XY coordinate. So a Z vector XYZ, if you have a vector, if I make these two 0, by removing these two components, I will be only left with the Z component, which is the Z. Right? Similarly, this is nothing but your R across I roof, R across J roof. Same thing, right? Yes or no?
Yes.
Okay, so this is how you convert. So now will you be able to convert any list of vectors into orthogonal vectors? So you will have n orthogonal vectors this way. Did everyone understand? Okay.
That's clear.
So now we are almost towards that position where we'll be trying to do some machine learning applications of linear algebra. So before that, we need to understand one thing which is called the normal matrices. So what are normal matrices? So you must have heard throughout for a long time that symmetric matrices are very useful, right? Symmetric matrices are useful. You may have heard. And you may have heard because they have orthogonal eigenvectors. Right? All these things you may have heard if you people who have done PCA and so on. But we will be here, what we'll be doing is we'll be dealing with a general class of matrices, of which symmetric and skew symmetric are parts of, Hermitian matrices are part of. So these are called or normal matrices. Why normal? Because you'll be breaking, whenever you're breaking them up, you'll be having normal components, right? Orthogonal normal components, right? Are you able to link all the things together? Because once we have orthogonal components, what is the use of it? So if you have orthogonal components, you can easily factorize them, right? Into eigenvalues and eigenvectors, which will help in applications like the PCA, which I'll be showing you in a while. Let's see. So normal matrices are defined as A Hermitian equal to A Hermitian A. This is, please pay attention here, because this is what we'll be using for the next 45 minutes to 1 hour, which is this definition that we have here, which is A Hermitian equal to A Hermitian A, given that A is a square matrix. Correct? So can you give me some examples without looking on the left side? So this you have seen, if A transpose is equal to A, you see A transpose is equal to A transpose A, right? This is one example, right? So symmetric matrix is a part of it, right? Similarly, diagonal matrix, there is no question of transpose and so on. So you will be having A transpose sigma is equal to sigma transpose sigma transpose. It is trivial. And skew symmetric, A transpose is equal to minus A into A. Similarly, A transpose will be A into minus A, which are both the same, right? Is this clear? So what are we trying to generalize? We are trying to generalize a class of matrices which are a superset of. So if this is your symmetric matrix, Hermitian matrices, Hermitian matrices, right? No, symmetrics के ऊपर होगा Hermitian. ऊपर ये हो गया. So this is Hermitian, and then you will have other classes of matrix: Q symmetric, diagonal, right?
Yes.
And we are trying to bring all of these under the same umbrella called a normal matrix. So what is the definition? The definition is AA Hermitian is equal to A Hermitian A. You see, do everyone see that this acts as an umbrella for all the type of matrices that you have heard are very useful, right? Okay, if you are happy with it, so now let's see some of the properties of this normal matrices. So we'll be showing, say a normal matrix A has n independent eigenvalues, lambda 1 through lambda n. We'll be showing that these following statements are equivalent. So can you tell me what does equivalent statement mean? So how many ways do I have to show to prove equivalence? How many proofs I have to do here? I just want you to revise some of the counting that we did in the first session. How many proofs we have to do? Equivalent means A would imply B, B would imply C, C would imply A, C would imply D, D would imply B, and D would imply A, and so on, right? A, B, B, C, so both sides, not only one side. Six of these.
2 factorial.
4C2, right?
4C2 into 2 factorial because both sides are needed.
Yes, so 4C2 into 2 factorial again. So you will be needing 12 proofs. Can you tell me a easier way? I don't want to do 12 proofs, no 12 proofs. So this is a question of logic and not maths. I'll show only 4 proofs and I'll be still able to do it. How can I do that? So if I can prove A implies B, B implies C, C implies D, and D implies A. Am I done?
Yes, because then we can use D implies B cycle.
Yes, so it's a cyclic proof. So whenever you need to prove, yeah.
But what about the proofs that come back? Because for equivalence we need to do, it's an if and only if type of condition, so we also need to come back.
Yeah, you'll be coming back. So you will be coming back from D to A, right? So you want to go to A to D, you can go this way, right? Yes or no?
Yes, the entire chain back. Yeah.
And then you can go to D to A. So A to D, D to A, both are done.
That done.
Similarly, A to B and B to A, both are done, right?
All cases covered, yeah.
Yeah. So if you have a cyclic proof, you can always prove the entire thing will be an equivalence. So let's prove it. So we'll be stating that A is normal. So we'll start off with A Hermitian is equal to A Hermitian A. So I'll be using this to prove B. So what is B? To B is unitarily diagonalizable. So what will I do to prove that? What is the step? Unitarily diagonalizable means just now we did. This is similar to a unitarily similar to a diagonal matrix, right? Which means I want to prove that A is U sigma U Hermitian. Yes or no? Unitarily diagonalizable. We have already done this diagonalization once. Can you tell me where? What is this? What are these? What does this mean?
It's similar. Similar matrix.
Similar, yes, but it's a special type of similar matrix. This is eigenvalue, eigenvector decomposition, right? Eigen decomposition. Yes or no?
Yes.
So here we'll be doing eigen decomposition with only using unitary matrices. That's the catch. So how will I do that? So do you agree I can write A as U T U Hermitian from Schur's triangularization? Yes or no? We have discussed it today. It's a triangular matrix. Right? So what will be A Hermitian? This will be U T Hermitian U. Yes or no?
Yes.
So what is AA Hermitian?
I.
Huh? How? Not I. A Hermitian is U T U Hermitian U T Hermitian U, right? It's equal to U T T Hermitian U, right? Yes or no? Right? Similarly,
So I consider T also to be unitary similar.
no, T is a triangular matrix. It has no property. So A Hermitian A would be similarly U T Hermitian T U, right? So now these two have to be equal. Correct? So for these to be equal, do you agree these two have to be equal because the outer ones are same? Yes or no? These are full rank matrices. So you have to have the inner ones which have to be equal. Yes, right or no? So you have to have T T Hermitian is equal to T Hermitian T. Right? Yes or no? Okay.
Yes.
So what does it mean? So triangular matrix, you have a triangular matrix, upper triangular matrix. So what is Hermitian of that?
So if we can say that T Hermitian equals T Hermitian T, so T is also not.
T is normal, yes, but I will show you it is only possible in one case. Let's see when. T is normal, of course, but that doesn't give me a lot of information. Yes or no? This is right? Agreed or not?
Yes.
Okay. So what is TT Hermitian? Can you tell me? So what are the elements of TT Hermitian? So first element, do you see is this sum? Yes or no? Correct? So you have say T11, T12 dot 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 T1n, right? Similarly, you have T11, T12, T1n because it's a Hermitian, right?
Yes.
So
Yes.
stop me if it is not clear. So T11, T12, T1n, T11, T12, T1n. Now do you see the first term TT Hermitian ka 1, 1? What is it? So it's summation of T1 square. Yes or no? I equal to TII square, I equal to 1 to n, right? This into this, this into this, into this, into this, and so on will sum up, right? Yes?
Yes.
And that has to be equal to, what is this first element? Only these two products, right? Because these are all 0. Correct? This has to be equal to only. Correct. So you see T1J, Tij, j greater than 1 square is 0. So do you see T12 equal to T13 equal to dot 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 T1n equal to 0? Do you see that?
Yes.
So all these elements will be 0, first row, except the first component, which is T11, right?
Yeah. Yes.
Similarly, you will have all the others also to be 0 except the diagonal. You can check this, right? Similar, same thing, right? T22 also you can check. Is it clear?
So it becomes a diagonal matrix.
Exactly. This is only true if this is equal to a diagonal matrix. So are we able to prove it? So now this has been converted to a diagonal matrix. So now we have seen A is UD U Hermitian. So it's unitarily diagonalizable. Clear? So we are really able to prove A to B. How will I prove from B to C? That the square of the elements of each of the matrix is equal to the sum of the eigenvalues. How will I do that? So how can I write this as Aij square? How can I write that as? Can you write this as trace of AA Hermitian? Just check. So you have A1, say you have A11, A12, A1n, A1n1 dot 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 ANN. A11, A12, A1n, AN1, ANN. So what is the first element in the first row? So product of these, what would be the product? A 1 component? It's gonna be A1 square plus A12 square dot 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 A1n square, right?
The summation A1j squared.
Correct. So you will have the JJ or II element will be IJ. Let me write I. So this is equal to summation of Aij square from j equal to 1 to n, right? Agreed? So if I want to take the trace of this, what does it mean? Trace of AA Hermitian would mean the sum of AA Hermitian II for all I equal to 1 to n, which is nothing but Ij A. Correct? Any doubt? I have found the one diagonal element as Brahmajit told me, and then I have summed over all the diagonal elements. So I have two sums, double sum, right? Agreed?
Yes.
One diagonal element is the sum of all the rows, first row. Second diagonal element will be the second row, and third diagonal element, third row, and so on. Good. So now what can I do to convert this to eigenvalues? That sum of lambda square of eigenvalues. This I will not tell you. You have to use this property, unitarily diagonalizable, and tell me in one line. So I have told you trace of AA Hermitian you have to show is equal to sum of the squares of eigenvalues. How will I do that? Simple. If it is unitarily diagonalizable, how will I write it? How will I write A?
We can write it as a U D U inverse, where D is the diagonal matrix of
Correct. Let
eigenvector.
me write lambda. Right? So because it's a, okay, let's write D only. Oh no, lambda is okay, na? This is eigen decomposition. Then trace of Q lambda Hermitian U Hermitian. Yes or no? This is what you told. This is A. This is A Hermitian. Any doubt? So what is U Hermitian? Is equal to I, right? Very good. So now you have U mod sigma square. So sigma into sigma Hermitian is nothing but all elements will be I square. Yes or no? Because it's a diagonal matrix. If you do not follow, tell me. Next, what would I use? I have derived this in the first matrix theory session. How will I convert this into trace of sigma square? If I can convert it into trace of sigma square, I'm done, right? So I'll put a question mark and I'll put trace of sigma square. Then that is equal to lambda I square. If this is true, it is true, right? These two steps are clear, right? Yes or no?
Yes.
Sigma Hermitian, this is equal to the product of the eigenvalues along the diagonal. You understand that? There's no question. But how do I get from here to here? Remember, we derived in the first day, trace of AB was equal to trace of BA, isn't it? They were
Yes.
cyclic. They were cyclic in nature. So what can I do to use this cyclic property? I will put it in front. I can put that.
So we can write trace this and trace U Hermitian into U lambda square.
Correct. This becomes
That will
I.
give you one unit matrix.
Good. So you have been able to prove B to C as well. How to prove C to A, C to D? Since U is, this is one liner. Since A is equal to U lambda U Hermitian, what does it imply? The eigenvalues are, the eigenvectors are orthogonal. Yes or no? Because we have had orthogonal diagonalizability. Because they are orthogonally similar or unitarily similar, right? From unitarily similar, you can show this, right? Yes or no? If you are a bit confused at why am I doing this way, just reorder these two. So do this prove as A to B, B to D, and so on. So tell me, how do I show A to B is done, B to C is done, C to D also will do. C to D, how will I do? Since it is the product of the sum of the lambda i's, which we have obtained from the unitarily diagonalizable matrices. This is true for unitarily diagonalizable matrices, that this is true, right? So that is true. What have we used? We have used this two product as the perpendicular eigenvalues, yes or no? Since they are perpendicular, we got the trace to be equal to this. Otherwise, we would not have got. Yes or no? Look at this step. These two were perpendicular, right? U Hermitian and U. So then since U Hermitian U is equal to I, what can I say? C to D. Then we can write A as U sigma U Hermitian. So it is unitarily. So it has eigenvectors that are perpendicular. You can also check it how, in what way? You can write A as AU as U lambda, right? Yes or no? From here, can I write this? Sorry. I just multiplied U on both sides. Okay. So U has U1, U2, Un. So AU1 is equal to lambda 1 U1, you're getting or not? 8 U2 equal to lambda 2 U2, you're getting. Correct? You got all these? And we know lambda 1 perpendicular to lambda U1 perpendicular to U2, Un. Correct? So all the eigenvalues, eigenvectors of A are orthonormal. Is this clear? Now, how will I prove D to A? And if it is not clear, please own up. Otherwise, I'll go to the next question. I don't want to ask the same question 100 times. So, if A has orthonormal eigenvectors, how to prove that they are normal? How do I do that? So if they have orthonormal eigenvectors, I can write this as U lambda U Hermitian. So what is A Hermitian? A Hermitian is which is equal to, yes or no? Correct? Similarly, A Hermitian A is, tell me. This is your A Hermitian or not? We have written A Hermitian. What is A Hermitian? U Hermitian?
U Hermitian lambda U. Lambda Hermitian U.
So what is A Hermitian? How do I do that? I do U. Tell me what is ABC Hermitian or ABC transpose? What is it? C Hermitian, B Hermitian, A Hermitian, right?
Yeah.
So what will you have here? A Hermitian will be U Hermitian. So this will go to the front. This Hermitian, sigma Hermitian, and U Hermitian. So this will convert to U Hermitian to U, sigma Hermitian and U Hermitian. Yes or no? So you have this as the A Hermitian, and then you have A, which turns out to be U lambda square U Hermitian. Is it okay? So do you see A Hermitian? So these two are same or not? No? Understood? Hence,
So for D, we have shown that A is normal.
yes. So having perpendicular eigenvectors means it is normal. Now we come to the application. See, PCA will take 5 minutes and SVD will take 15 minutes. Let's see. So PCA, what it does, say you have n data points, right? So in general, in machine learning, you have features over r to the power, say 10,000. For example, if you have an image 256 by 256, so your vector will be of the order of 256 by 256, which may be difficult to train a model with. So generally, what people will do, at least people used to do, is convert this into a, say, R10 dimensional, right? And this was done using a PCA, which says they are called the principal components. How do I get the principal components? So do you have an intuition by seeing these data points for a classification, or where will in which direction will the maximum information be retained? In which direction will maximum info be retained? I'll give you a very extreme case scenario. Say we have a line and all these points are on this line. So what is the data? What are the data points? Your data points are y, x, comma, y equal to, right? But I could have, if I convert this to be the new x-axis, do you agree I will get only one dimension, say d1, d2, and so on, dn? Yes or no? So all
Yes.
these points have here x and y, but since it is lying only in one-dimensional subspace, right? It is not lying in a higher dimensional subspace, writing in a one-dimensional subspace, which is a line. Yes or no?
Yes.
So what can you see from this figure? Which, if I have to throw out one component, which component should I throw out in general?
If you have converted that line to the x-axis, we'll throw out the y component.
So you see there is a trend in this line or not along this component. There is maximum variation here, right? As we saw in best fit problem previously. This is the axis of maximum variation. Yes or no? From the figure, can't you see? So all the points are situated along this line, and there's a small perturbation towards the other component. This is a PC2, this is PC1, right? Okay. So if I retain PC1, do you see that I'll be only throwing out a small information? That is this error. This will be my error every time I throw it out, compared to if I throw out PC. See, now I'm using only PC1, right? So if I use PC1, this is the error vector. Similarly, if I use only PC2, what will be the error vector? This will be the error vector, right? E2 is clearly greater than E1, right? It can be much greater actually. Yes or no?
Yes.
So for all these data points, your errors would be very high along the dimension where is less variation. Yes or no? Errors, we want to retain the axis of maximum variation. Is this motivation clear? I'll show you another motivation as well, which you will be doing as a homework in your assignment. But is this motivation clear? That you want to retain the direction of maximum, right? Maximum variance of the data. Okay. Since there's no more question, we'll start. So see the first thing which I'm doing over here is I'll be computing the mean of the data point. So if I compute the mean of the data point, empirical mean, do you agree will be expected value of x will be 1 by n summation of I equal to 1 to n xi? Yes or no? You have n data points. This is your expected value, mean of the data point, which let us write it as mu cap. Correct? And tell me, What is the mean of the data points? This is the mean, yes or no?
Yes.
Okay. What is the variance of the data points? What is the covariance matrix? Covariance matrix of X we discussed. So covariance of X comma Y, how did we find? We found it as expected value of XY minus expected value of X into expected value of Y, which was also equal to X minus Y into X minus mu X into Y minus mu Y. You recall? Yes or no? So if there are n dimensions, what will this be? Your covariance matrix for n dimension turns out to be X minus mu X. So X minus mu transpose. So you have n dimensions. So I have stacked all the vectors x1, x2, dot, dot, dot. So X and Y, if I stacked, I'll give you a small example. And this is another, right? Right? What will you have if you have this? Say you have your mean is 0 and all. So what is the product? You have a matrix called x square, xy, yx, y square. Yes or no?
Yes.
So this is your x, this is your x transpose, say. So what is the first? So if I take expectation over this, what will I get? Expected value of x square, expected value of xy. Assume mu x equal to mu y equal to 0 for this time being. You can always do without that, doing that. Expected value of xy, expected value of y square. So what do you see? Doing this, you get the covariance. This is the covariance of xy. And this is the variance of y. Yes or no? We have discussed this, right? So your element ij will be covariance of xi comma xj, right? The ith random variable and jth random variable, correct?
Yes.
So this is your x, this is your covariance matrix. So which can be sampled as, if you have data, so you do not know the distribution, right? You only know the data. So you will be using the sample covariance matrix, yes or no? Right? Is this clear? So this is how you define the mean and the covariance of a data. This is why I wanted to tell you. So what do I want to retain? I want to retain the information of the maximum variance. So how can I do that? So you tell me, what would be the, so say I am going to use the only the first principal component. First principal component only. So if I use the first principal component only, what will be the new data points? See, look at this. So I have only one principal component, which is the unit vector. Mod of u1 is 0. What am I writing? 1. And you have a vector v. So what would be the component along the u1? V along u1 would be, say let us write z1 as v along u1. So what will it be? So we have x's over here. Let's write x only. Tell me, how will you take a projection of x on u1? So I told last time, like projections are one of the most important things. What will be the projection of x1 on u1? u1 transpose x1, right? Yes or no? Yeah, I think this is trivial for you. So z1 will be u1 times x1. So what would be the mu z now? Mean of the New principal component will be 1 by n zi's, which will be 1 by n mu I transpose zi, which will be what? Mu1 transpose 1 over n zi, I equal to 1 to n. So what is this? Zi bar. This is your U1 transpose Z1 bar, right?
Yes.
So what will I do next? So this is my Z mu Z. How will I get the sigma Z or the variance of Z? So variance we have, variance of Z we get as, since Z is a scalar here, right? So we can use our old formula, Zi minus Z bar square. Yes or no? My word. Why am I not able to explain? Or you are not understanding? I'm going very slow, right? So mean of all these projected data points I have got, and I want to project it along the direct dimension of the maximum variance. Yes or no? So I want to
Yes.
find u such that it maintains the maximum variance. So what does this mean? Z minus Zi minus Z bar. It means expected value of. So how will I write this? Half times summation of I equal to 1 to n. Your Zi minus Zi bar square. Clear? There's no difficulty in this. So I'm writing this as a sample mean. Stop me as soon as you think it is difficult. So Zi would be, what would be Zi? U1 transpose X, yes or no? Yes or no? This is the first principal component. We have written Zi to be U1 transpose X. Minus Zi complement would be transpose this one, right? So mu Z bar is given by, what is this given by? We have already found this, right? This is 1. And where is that complement? Yeah. So mu Z is given by this. That's what mu Z. I've written not Z bar, but mu Z. So mu Z is given by U1 transpose. Here I don't, why did I write Zi's? These are Xi's, right? So you're not following. So I'm projecting these, right? So I'm taking the mean of the data. So this is the data that I'm projecting. I wrote the projection value here. You didn't tell me. This is Xi bar whole square. I equal to 1 to n. So how can you write this? Any idea? How can I project it backwards? So since these are scalars, right? So you can write this as Xi minus, what can I write this as? U1 transpose Xy bar into U1 transpose, or you can write this way also, right? X1 transpose U1 minus X1 bar U1. Yes or no? Square I'm writing 2 times. Is it okay?
Yes.
So now what will I do? Tell me. So I can take U out, yes or no? If I take U out, what will I have? U1 transpose x1 minus x1 bar or x bar, what is full mean, and you will have xi minus x bar transpose U1. Yes or no? Is this step clear? I have taken U out, I have taken U common in this side and this U1 common from this side. So what is this matrix? I already showed you before. This is the covariance matrix, right? Covariance matrix of X or not? Sorry. Yes or no? Wait, it will come. Yes. Covariance matrix of X is defined by expected value of X minus mu minus into expected value of X minus mu transpose or not?
Yes.
So is this the covariance matrix of the data or not? That we have at the end. Is this the covariance matrix of the data? So we will have U1 transpose sigma X U. So what are we trying to do? We are trying to maximize arg max over U, U1 times sigma U. This will give me U star or U1. What is the constraint that you will have? U1 is equal to 1 because it has to be a unit matrix. So first day I will discuss Lagrangians with you in the 9th session. But for this, for optimizing this, what did you do for optimizing a function? You took the derivative and set it to 0, right? Yes or no? For getting the maximum or the minimum of a function, you get the gradient to be 0, right?
Yes.
So for a constraint optimization problem, your loss becomes, or your objective becomes some lambda times 1 minus this. So this is called the Lagrangian multiplier. We'll see this in the 9th session. Why is it? So you will have dl du as sigma u minus. So you will have y square equal to 1. Equal to, so I'll show you this in the last class, but anyway, so this is just a quadratic. So this is a quadratic as we discussed before. So you quadratic, the derivative of a quadratic is always equal to the 2 times that, 2 times the component. So what did you get? You get mu into sig q equal to lambda u. What do you see from this? So what do you see this? What is this? What equation is this? The eigenvalue eigenvector equation, right? This is how I started eigenvalues and eigenvectors. Do you recall?
Yes, sir.
So how will I what will it maximize it? Can you tell me? So I'll put this in the equation. So lambda u. So I will have lambda u1. So you will have lambda u1 square. So arg max will give me lambda. So u1. So you tell me how will I maximize this? How will it get maximized? So this becomes 1. So I have left with lambda. So which lambda will I select to make the equation maximum, to get this maximum value for this? To get the maximum value for this, which lambda will I select? So I have a set of how many lambdas? For a matrix n by n matrix, how many lambdas do I have? How many eigenvalues? N eigenvalues. So I will select the maximum eigenvalue. So I will definitely select lambda max to maximize the objective. I'll select lambda max to maximize the objective. So what will be u1? The first the u1 will be the eigenvector of the first eigenvalue. So any idea how will I get the second principal component, the second eigenvalue, and the third eigenvalue, right? So the components of these are equal to, jth components are equal to the jth eigenvalue. So I will give you a homework, which will be in your assignment as well. Show that the same result hold if you are trying to maximize reconstruction. What is reconstruction? The reconstruction error would be, what is the reconstruction error over here? Your vector V minus U1 transpose V times U1, yes or no? This is your error?
Yes.
This is your projection into U1. So I am saying you will have to show that the error is minimized try this. You can take the help of the internet also. But anyway, this is very simple. So you will take the summation of I equal to 1 to n, and you will show that this is minimized for sigma u sigma. So you'll get the same equation. I gave you the intuition using this picture, using this equation also, which maximizes the reconstruction. You will also get the same equation. So to end today's session, I'll be giving you the most important tool for any software in matrix theory, which is known as the singular value decomposition. What is singular value decomposition? Just let us draw a picture, and that will be enough. I will not go into maths details, so I'm seeing you're not understanding, so we'll not go into that much of a detail. So let's see. So you have something called we have discussed this, right? Something called the row space. Say you have a matrix M cross N, where N is greater than M, and you have the rank of the matrix is equal to R, which is less than minimum of M comma N. So this is the definition. So we all know that rank is always less than equal to the minimum of the both. Anyways, so we know row space of A and the null space of A are perpendicular. We have shown this in the classes many times last 2 days. And we have also shown column space of A and column space of A transpose to be orthogonal. Yes or no? Right? Now you tell me, AX, what is this vector? If I do a vector matrix multiplication, what is X in? Do you agree X is in the row space or the null space of A? X belongs to row of A or null space of A, because X is n dimensional, right? If you want to draw the picture, M cross N matrix, yes or no? X is n dimensional or not? For multiplying a vector with a matrix, it has to be equal to number of columns. Okay. So you say you have a vector Q1, right? So when you multiply A, what happens? Do you agree? A U1 will go to the column space or not? So a matrix vector multiplication is a linear combination of the columns, yes or no? So since you have no doubt, so you know that AX is sum AI times XI for all I between 1 to n. So you will have n orthogonal. If you take n orthogonal components, so all orthogonal components won't work. So U1, U2, say R of these such that they have orthogonality in this space as well. V1, V2, VR. Do you see what will be the help? So I will have something like AU1 is equal to sigma 1 V1 and AU2 equal to sigma 2 V2 and so on. AUR is equal to sigma R VR. Yes or no? And if they are orthogonal, how will it be helpful? I will show you that there is a solution that exists for making it orthogonal. But how will it be helpful in some way? See, if I stack the U1s, so to UR, U1, U2, UR, which are all n-dimensional, right? I'll append these later. So can I do something like sigma 1 V1, sigma 2 V2, and sigma R VR? Yes or no? Right? I'll append this a bit later. The same way as we had described for an eigenvalue decomposition. Okay, so you can write AU. So this is R dimensional, R columns. So how many would be in the null space of A? Do you agree there will be n minus R columns? So the rest of them, yeah, go ahead. So you'll have n minus R columns in the null space of A. So you can get the null space vectors as n1 dot 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 n minus R. So I will get a n cross n matrix, right? Which will give me zeros here, n minus R columns of zeros, right? So I will also be, so this is equivalent to writing some V matrix, which will be what? V will be V1, V2. So why are you not interacting? I'm just doing singular value eigenvalue decomposition again. And sigma 1, sigma 2, sigma R. Yes or no? Sigma 2 dot 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 sigma R. And rest of them I will make zeros. Right? I don't need. So V can be, the rest of them could be in the which space? So VR is in the column space, right? So which space will you add these? You will add them. So M minus R of them you will add in the null space of A transpose. So VR plus 1 VM. So you see, you get a decomposition something like this. A, which is an M cross N matrix. For any M cross N matrix, you get N, which is a N cross N matrix, V, which is a M cross M matrix, and you get a sigma matrix, which is M cross N. You will augment it with zeros accordingly. So this is, you see, this, how many columns do you have? You have M columns, right? So you can, and you have M rows. So number of rows you can add with it is N minus R. So this is your N cross N dimensional covariance matrix. So you can convert this into V sigma U Hermitian. This is what I was telling. So you see, you can, any matrix can be written as this form such that all the singular values are positive. So as I have shown you in this case, you append zeros in case n is more. And similarly, you append zeros below in case of n is less. So that is the geometry of the singular value decomposition. Now I want to show you why is this true. So is this clear what I did here? And I will show you two things. So A is, so you can write it as V sigma U Hermitian, right? So what is A Hermitian? A Hermitian A? Can you tell me? We are almost done. Just bear with me for 2 minutes, then we'll be done. What is A Hermitian A? So A Hermitian A will be U sigma squared U Hermitian. Yes or no? Right? So what can you say? You can say sigma 1, sigma 2, dot, dot, dot. Yeah.
How does this happen? Hermitian A.
This is clear, right?
Yeah.
So what is A Hermitian? U sigma Hermitian, V Hermitian. Yes or no? So
Yes.
multiply A Hermitian A.
Okay.
So what do you say? So these are the eigenvalues of A Hermitian A, and U's are the eigenvectors of A Hermitian A. Similarly, V's will be the eigenvectors of A Hermitian, and so on, right? But be careful, the eigenvalues, they are scaled to some positive or negative. Since they are squared here, you may not be able to, the eigenvectors may not be exact, may not have the exact sign. So you must be able to always do A sigma I is equal to this equation. You must be able to follow to get the sign of VI's. So anyways, we will see why is this, why can you always get these perpendicular matrices in a short presentation. So I will show you that A Hermitian and A Hermitian A have the same eigenvalues. Can you tell me how you can show that? So I have shown you. So if I can show that, we will be done. Yes or no? So A Hermitian or A Hermitian A is what we wrote. I don't remember. Yes, A Hermitian A we wrote as U Hermitian or U sigma square U Hermitian. Yes or no?
Yes.
So similarly, I can also write A Hermitian as V sigma square V Hermitian. Just check. Right? A Hermitian will be, what will be A Hermitian? V sigma U Hermitian. And then A Hermitian from here will be V sigma Hermitian and V Hermitian. Yes or no? So V sigma square V Hermitian. Right? Correct?
Yes.
So now what will I do? I will replace sigma square as A Hermitian, V Hermitian, V. Correct? Is this right? I'm multiplying V Hermitian on both sides. Understood? Very simple, right? So now you can put this value in the first equation. Do you agree? So what will I get? I will get A Hermitian A as U V Hermitian A Hermitian U Hermitian V. Correct? Yes or no? So just can you tell me the product of, there is a theorem would be product of two unitary matrices is unitary. How can you show that? So U and V are unitary matrices, say. So how can you show that the product of their unitary matrices are unitary? You can directly take the Hermitian, right? Say U and V are unitary matrices. So what will you get? You'll get V Hermitian, U Hermitian, UV, yes or no? Which is equal to V Hermitian V equal to I, yes or no? So it's not yet appeared, so I'll just wait. Yeah, is it okay? Is this a line okay? So if U and V are unitary matrices, their product also will be a unitary matrix. That's what I have shown over here. Good. Then do you agree that A Hermitian A can be written as W? This is some W. A Hermitian, W Hermitian. Yes or no? This is some Hermitian, this is some unitary matrix, and this is the Hermitian of that matrix. So you can write this as WA into WA Hermitian. Yes or no? Correct? I hope this is okay, right? I've just factorized these two terms this way. The last two terms. What can you write this as? You can write this as A Hermitian W Hermitian W A. What is this? This is equal to WA Hermitian WA. So did you get some insights now? And these two are equal. So what will it mean? What does it mean? That WA is normal, right? Yes or no?
Yes.
If WA is normal, so WA is normal means it is unitarily diagonalizable.
Yes.
So I can write WA as some X. Yes or no?
Yes.
So A can be written as some W Hermitian X sigma X Hermitian. Yes or no?
Yes.
Right? Now sigma is all the eigenvalues, right, of WA. Yes or no?
Yes.
So if I convert this to this form, lambda 1, lambda 2, where I only take the magnitude, I can do that. And I will have another diagonal element D. This is your say mod sigma. And I will have another diagonal element which will be e to the power of I theta, e to the power of I theta 1, e to the power of I theta 2. I can do that. So any lambda I can be written as, recall your class 11 complex numbers. Yes or no? Any complex number can be written this way or not?
So the D matrix that we are taking.
Yes.
So why are we taking this? What are we doing with this complex number?
So these can be complex numbers, right?
Yes.
So I don't want complex numbers as singular values. I want them to all be real numbers which are all positive. Understood?
Okay.
Right. So to do that, I will be taking this mod and I'll be doing this, right? So this is my any complex number. Do you agree?
Yes. Yes.
Good. So now I will be writing this as, so this I can write this as some, let us write this as some V and this as some U. And I will write sigma Hermitian as sigma Hermitian and D. So now D will just scale the U's, right? That's right, keep it X, and D will just scale the columns. It will not do anything to their perpendicularity or something. They will not do anything to that. So what will happen? I'll be left with this. I will write as sigma, and I'll be left with, what is this going to be? U Hermitian. So this exists, I wanted to show in a mathematical way, because we were confused that these perpendiculars may not exist, right? So whenever we take something in the row space and they are perpendicular, then it may not be perpendicular in the column space, right? When once we do the product. Agreed? So but this guarantees that there is a solution. This analysis guarantees that. Do you see that? So any matrix can be written in terms of A sigma VH Hermitian, where these are all greater than 0 up to the rank, and then you can have zeros. Is this clear? If this is clear, there's no more questions. We have come to the end of matrix related stuff. All the linear algebra is done. Next day, what we'll do is we'll be trying to do what is called as norms, where we quantify, where I think somebody had mentioned norms somewhere, L2 norm and L1 norms. So we'll be doing those next day, where we'll be trying to measure what is the amount of energy in the matrices as well as vectors. Please revise and come, because today we had gone very slowly, and if you have not understood something, feel free to ask me now, or over email, or in the Teams group. You have a student discussion dedicated place. You can ask there. Let me just stop recording. Okay, so we have a dedicated